Hello friends, welcome to my channel. Let's have a look at problem 687, longest Univalue path. In this video, we're going to share a solution based on recursion. Here, we're going to use a treatment same as in the video for the problem 124. So Leetcode 124 is binary tree maximum path sum. So the difference is that in problem 124, so we consider path sum, but here we look at path length. So the solution present here will also have the same code. So notice the quotation mark in the same. So before we look at the statement and the analysis, let's make a comment. So this is a classic or fundamental problem. So it's good to genuinely understand it. For this purpose, we're going to write the code with some redundancy for clarity and readability. First, I'll read through the statement of the problem to digest the requirement, and then we present the idea, and finally we share the code. Given the root of a binary tree, return the length of the longest path, where each node in the path have the same value. So this path may or may not pass through the root. So the length of the path between two nodes is represented by the number of edges between them. So in other words, the length equals the total numbers of nodes minus 1, right? So here are two examples. So in example 1, so the return is 2. So the corresponding path is 5, 5, 5. So the number of nodes is 3 and the length is 2. So in example 2, the return is also 2. The corresponding longest Univalue path actually is 4, 4, 4. The highest level is this one. So then all the other levels are at level 2 in this tree. So before we look at the idea, let's look at the constraints, or we can see the additional assumptions. First, the number of nodes in the tree is in the range 0 to 10 to the power 4. So it means that the tree can be a null tree, and the 10 to the power 4 actually defines the problem size. Secondly, the node value can be negative, right? The elements or the node value is in between negative 1000 and positive 1000. And the last one also quantifies the problem size. It says that the depth of the tree will not exceed 1000. So this is the statement of the problem. So now let's look at the idea. So actually we are going to use exactly the same logical structure with problem as problem 124. So here the idea is that for each node we are going to compute again two pieces of information. So we can represent this as a function relation. So given node, we are going to output L and R. So the interpretation of L and R are the following. First, L means the number of nodes in the longest Univalue path starting from the node and next going to the left subtree. The R is the number of nodes in the longest Univalue path starting from the node and next going to the right subtree. So before we go further, we make a remark first. So here for each fixed node, we only care about going to left or right for the current node. We don't care the direction from child to its descendants and onwards. So this set of two pieces of information will enable us to find for a given node the number of nodes in the longest Univalue here I will see. Univalue path that passes through the node and with the node being the highest level node in the path. So here the highest means smallest level indexing. For example, root is at level 0 and its children are at level 1. So as the Univalue path passes through the node, So certainly the unique value is the node value. So in order to compute this information, in other words, we are going to compute the number of nodes in the longest Univalue path passing through the node, and with the node being the highest level node in the path. We are going to look at the information of L and R corresponding to the node's children. So we are going to define LL, LR as F node left, and similarly for node right. And also, as in problem 124, we are going to introduce little m, which is the max of the L and R for the left subtree, and capital M will be the max of the L and R for the right subtree. And then we are going to initialize number nodes to be 1 for counting the node itself. Then we also temporarily set LR to be 1 to get LR to the node itself. Then what we are going to do is to check if the node left exists, if the node left value equals the node value. So similar for node right, right? The condition is a 2-if, right? The first if says that if the left subtree of the node exists and the node value, the value of node left equals the node value for the node itself, then actually we can extend the Univalue path to the left subtree. So we are going to increment the number nodes by m, and then we are also going to increment the L by m. So similarly for the right subtree. So if the right subtree of the node is not null, and the node right value equals node value, then we can extend the unique value path to the right subtree. Then we are going to add the number node, that is m, right? So also we are going to introduce, so we are going to update the, so here is a capital M. So that's the two if conditions. So then actually the end nodes is the end nodes in the maximal univariate path passing through the node, and with it being the highest level. So after we doing the increments, so the final state of LR contains the two pieces of information for the node. So this is actually a recursion picture. So our plan will be the following. We will write the hyperfunction f to do the above job, and in the process we're going to update the number of nodes for the Univalue path, and finally we return property. So here the return should be the length of the path, right, not the number of nodes, but the relation is simple. So with that said, actually we can look at the code. So for this purpose, because we want to continuously update the number of nodes, I'm going to introduce an attribute. Let's call it answer. So this answer to be first to be 0. So this number of nodes in the path in a Univalue path. So we want to find the maximal ones. So here I'm going to define this hyperfunction and given a node. So we are going to compute the two pieces of information LR for this node, and in between we are going to update the answer attribute. So with that said, first let's consider a stop condition or edge case or base case. If not node, so we're going to return 0, 0, right? So there's no corresponding to no nodes. And otherwise, so we can get the information for the left subtree, that is f node left, right? So notice that if node left is null, so this corresponds to 2 zeros. So similarly, we can get the information for the right subtree, that is node right. Then we want to use these two sets of information to get the L and R for the current node, right? So for that, so I'm going to introduce the little m and a capital M. So for as in problem 124. So in some sense, it's not absolutely necessary. However, our purpose here is not to write shortest code. So we want to expose the idea and the logic more clearly. So we introduce little m and a capital M, And then first I'm going to set the max length to be 1. So the max length will give us the max length, or so max number of nodes, actually I would say max. So let's call it n nodes. So it's the number of nodes in the path, longest path, passing through node, with node being the highest level node. So also I'm going to first initialize L and R to be 1 and 1. So here all these 3 ones are counting the node itself, right? So then let's check the 2 if conditions. If node left and node left value equals node value. So in such a situation, so we can extend the Univalue path to the left subtree. So in this case, the number of nodes can be incremented by that in the left subtree, that is little m. And also we're going to introduce this L by this m, right? So this is one case. So we check the left subtree, and then we're going to check the right subtree parallel, right? Node right and node right value. So if it equals the node value, it means that so we can extend to the right subtree also. So n nodes is incremented by capital M, and R is incremented by capital M, right? So once we got this information, so actually we should update this this attribute. So self answer equals max of its previous state, and then we're going to use the current number of nodes, right? So what we are going to return for this node is nothing but return and L and R, right? So this finishes the function. So this function actually plays 2 roles. First, the overall purpose is compute the 2 pieces of information specified above, that is L and R. And in between, so if we find a longest unique value path, we're going to update the self answer attribute. So here the n node is the number node in the corresponding path. So next we're going to call this function. So if we're going to call function, so we call it and with the root as argument, and then we're going to return the length. So for this purpose we need to return overall, so self answer minus 1, right? So that's the length. This is the number of nodes. However, the length cannot be negative, so we're going to return this one at 0, right? So if we just have a single node tree, right, the longest Univalue path is length 1, right? The answer should be 0. So with that said, let's first do a check. Yeah, it passes the example. So now let's look at generic case. Yeah, it passes all the cases. Let's check again. That should be reasonably fast. So with that said, I guess that's about it for this specific problem. Actually, this problem can be solved in a number of ways and different formats. So for the video here, it's good to compare the solution in this video with the solution for problem 124. So actually the 2 solutions share exactly the same format of coding. So with that said, I guess that's about it. Thank you.